All right, let's get started. Hello, everyone. Welcome to today's talk. I'm very happy to introduce Kevin Eo from Google and Columbia. So he's a research engineering manager at Google and a PhD student at Columbia. And his team, Kevin's team at Google, has been doing a lot of very interesting deployment of cryptography in practice, like using private set intersection or fully homomorphic encryption and so on. One notable example is the password leakage checkup on your Chrome browser or Android phones. And Kevin has done a lot of research from theory all the way to practice, in theory, theoretical crypto, applied crypto, and security. And he has won 2 distinguished paper awards from Usenix Security. And after all these years of research experience, he finally decided to go get a PhD degree. So, although in my opinion, he's a very mature, independent researcher, he's officially just a second-year PhD student at Columbia. Today, he's going to tell us something about some of his more theoretical work on oblivious RAM.
Thank you for the intro. Yes, so I think this is a theory seminar, so I'm going to focus mainly on the theoretical stuff and talk about nothing about the applied. If you have any questions about that part, feel free to ask me later. So in this talk specifically, I'm going to talk about cryptographic data structures. So really the interplay between data structures and cryptography. In particular, I'm going to focus on a lot of my work mainly on limitations and lower bounds. And at the end, I'm hopefully going to give you some open research problems to overcome some of the limitations that we know today. And because someone asked, you need no prior knowledge in cryptography. In fact, a lot of this talk will focus more on the algorithms as opposed to the crypto. All right, so here's an outline of what I'm going to do. I'll first tell you what are cryptographic data structures. I'll talk about the interplay between 2 specific primitives called oblivious RAM and encrypted search. I'll give you an idea of one proof technique, and I'll also tell you about some frameworks that you could use to prove lower bounds if you're interested in it as well. Hopefully I have enough time to go through everything, but I'll try to go quickly. All right, so what are cryptographic data structures? They're sort of, okay, let me first of all give you a very simple view of how I view data structures. It's not all-encompassing, but it gives you an idea of how to go from data structures to cryptographic data structures. So in a standard data structure, you have some CPU, or computing unit on I guess, your right, as well as some memory unit on the left. The CPU gets some query, and will essentially probe parts of memory to be able to answer the question you want. So for example, you can think of this being a query into a binary search tree, and the binary search tree is stored in RAM somewhere. And sort of one way to sort of upper bound the cost is to see how many memory accesses you touch. So when you have a cryptographic data structure, it's the same setup. But essentially what we assume is that the RAM unit, or the memory unit, is adversarial, in the sense that it's sitting there and it's going to be able to see everything that the RAM would see. For those who have a little more knowledge about these areas, one way to view this essentially is to have the CPU be something like a secure enclave or a hardware secure module, and RAM is the untrusted memory essentially. So this was actually the original motivations for some of these problems. But in the modern day, I think there's a slightly more interesting approach via the cloud, where essentially you can sort of, instead of viewing this as a computing unit within a machine, you can view these as user devices that sort of offload or outsource storage to a cloud storage system. So in maybe a more reasonable approach, and the way we're going to talk about it throughout the rest of this talk, essentially is you have user devices that own data and outsource them to some cloud storage system who may or may not be adversarial or who may or may not be watching. And the goal essentially is to provide privacy for the user devices and their data. That makes sense? Okay. So then next question you should ask is, what should we protect? Right? We're talking about cryptography. What do we want to actually hide? The first natural thing to think about is to hide the contents of the data structure. Whatever the data structure stores, we want to store from the adversary, or prevent from the adversary seeing. It turns out this is not too hard. So for example, let's suppose you had documents and you uploaded them to your cloud storage system, whatever storage, Dropbox or whatever. It turns out if you wanted to just hide the documents, it's pretty easy. All the client has to do is keep one private key and simply encrypt everything before it's uploaded. Right? And simultaneously, if you wanted to download an encrypted document, you just download the encrypted document and decrypt locally. So this ends up being very simple. If you wanted to just protect the contents of the data, this is not a very hard problem to do in data structures. Okay, so I think that's the end of my talk, right? We're done? That's it. Now, it turns out that there's other things that you really want to hide that are really hard to hide. In particular, What we really want to hide, or what turns out to be very challenging, is to protect the queries that are performed on the data structure from the adversary. So this is the canonical example I'd like to give, which is the following. You have these encrypted blobs. You don't know what the insides of the blobs are, but maybe I can color them. I know the top document is a blue blob, and the bottom document is an orange blob, right? And then consider two different types of accesses. In the first one, I'm going to access the blue document twice. The adversary doesn't know what the contents of the document are, but it sees, okay, you're downloading the blue document twice. And the other alternative is simply this, where I download the blue document and the purple document, that's the orange blob, each once. And the adversary can clearly distinguish these two. It doesn't know what's going on inside, but it knows what you're doing with the data, essentially. And this is what we call the access pattern, or sort of the queries. And it turns out the whole goal of cryptographic data structures is, in many cases, actually preventing or protecting the queries performed on the data structure from the adversary. Because this ends up being harder. And in fact, somehow, if you don't protect this properly, it turns out you can actually leak the contents of the data as well in the future. And somehow there's like an interplay between this. Actually, I think Roberto has some work on this kind of stuff as well. So it turns out that this is the key problem that we're going to study throughout the rest of this talk. All right. Any questions on cryptographic data structures, or else I'm going to go on? All right. So the most famous primitive in this line of work was called the oblivious RAM, which you could think of, in other words, as a cryptographic array, literally. So how does an oblivious RAM work? Again, I'm going to use the cloud setup here. So I have the user device on the right, as well as the cloud storage or adversary on the left. What happens essentially is the user device has some private key, and it's going to outsource an encrypted version of an array to a server. And in particular, what's going to happen is you might get a read operation. Let's say I want to read the first entry. I'll do a sequence of complicated operations to try to hide that I'm reading the first entry and to get sort of the first entry. But in a sense, I wanted to point out that these oblivious RAMs are very stateful. So what ends up happening is after these operations are done, or during these operations, the key will be changed. And not only will the key change, in particular, the array will be re-encrypted, the array will also be permuted. So when you think about encrypting the array, not only are you encrypting each element of the array by itself, but the encryption also includes permuting and hiding and obfuscating how the array is stored on the server from the server, essentially. Okay, additionally, oblivious RAMs also allow writes. So in a sense, you want to be able to do both reads and writes obliviously. So the queries are actually reads and writes, and you want to be able to hide what's going on. Okay, so I told you sort of the functionality and what an oblivious RAM looks like and how stateful it typically is. I haven't really told you what the security is. So here's the formal definition. It's quite long, but very high level. What it essentially says is, consider any two equal length sequences of operations that a data structure could have performed. Maybe it did 5 operations here, 5 operations there. And what this complicated definition essentially says is, in the view of the adversary, whatever the ORAM reveals about the operations of the sequences should be indistinguishable. In other words, if I had run 5 operations for one type of operation, O1, and another operational sequence of length 5, the outputs that the adversary sees should be the same in a computational setting. So the adversary is computational. So what does that mean in that previous view? Essentially, what is the adversary's view? It turns out that everything in the red box is the adversary's view. So the adversary sees all the interactions between the client and the server, and it sees everything stored in the server's memory. Clearly, it can't have the private key. If it has the private key, there's nothing we can do. But sort of, this is what the adversary sees. And what an oblivious RAM is trying to do is say, if I did read 1 or read 2, or any sequence of 5 operations, all the adversary knows is that you did 5 operations and nothing else. Any sequence of 5 operations should be equally likely possible from the adversary's eyes. Very good. All right. So this talk is more about lower bounds, but I have to give you some upper bounds. So it turns out that this was started from 1996, actually. So Godrek and Ostrovsky actually invented oblivious RAMs in 1996. And there was a long line of works up till about 2015 that were stuck at about log squared and overhead. So one of my works actually in 2018 was to show that there exists an oblivious RAM with essentially logarithmic overhead. So this was in Fox in 2018. And it turns out afterwards, others were able to shave the log n factor too. So now the best constructions that appeared in 2020 are that we can do oblivious RAMs with logarithmic overhead. So what does that mean? So in a standard array without cryptography, you access a single entry using one memory access. Now we can do this with log n accesses, essentially. But now you get this very strong oblivious property that you can hide the sequences that are occurring. Yep.
This is for both.
For both read and write, exactly. Yeah, yeah. So these are fully dynamic. Okay. So now I keep talking about oblivious RAM, and you might ask, why are oblivious RAMs so important? And it turns out they're really important for this very simple composition theorem. In particular, what this says essentially is that if you take any data structure, any plaintext data structure without any cryptographic guarantees, let's suppose it had overhead T and space order n, then you can use an oblivious RAM to create an oblivious version of that data structure where the only difference is that the overhead, or the query overhead, goes from T to a multiplicative factor that depends on the ORAM, on the time of the ORAM itself. At a very high level, anytime the data structure does an access into memory, which you can view memory as an array, you replace it with an ORAM, right? So using the best ORAMs, essentially, you can get, for any data structure with overhead T and space n, you get an oblivious counterpart with exactly an extra log n factor multiplicative in the query overhead. Go ahead. Good, because of, so what the overhead here T means is that you're doing T memory accesses. So I have to replace each of these memory accesses with a log n. So it becomes T times log n, right? It's a multiplicative. If it was additive, it would be good, actually. Like, I wouldn't even need to do all this work. But so it turns out, this is not bad. Theoretically, this seems pretty good, but, we're greedy. Can we do better than log n, right? So essentially, this question then becomes a question about ORAMs. Can you do an ORAM with better than log n overhead? So there was a seminal paper in 2018 by Larson and Nielsen that actually showed this is impossible. So in the CellPro model, all oblivious RAMs require logarithmic overhead. All right, so side note here, what is the CellPro model? Let me get into that quickly. So like for you to understand this lower bound, we have to figure out what the model is. So in a sense, the CellPro model is the following. It was invented by Yao, I think in the 80s, actually. And it's a very, very weak cost model, which means it has very strong lower bounds. In particular, the CellPro model takes all the server's memory and splits it up into W-bit cells. And the only time we ever charge you any unit of cost in the CellPro model is when you access a single cell. So if you access a single cell, it costs you 1 unit of cost. And that's it. That's the only thing we charge you. Everything else is free. So literally, you could solve the halting problem for free. You can solve your favorite P versus NP problem for free. Or no, solve your favorite NP problem for free. Generating randomness, accessing the random oracle, all free. Accessing client storage, all free, right? But what this means is that if you consider this very weak cost model, it implies very strong lower bounds, right? Any lower bound we prove in the CellPro model should apply to any realistic model of computation that we consider in the real world, where these things would actually cost you, right? Okay, so going back to that result, essentially, what they essentially said was that the oblivious RAM can't have lower than logarithmic overhead, right? But in a sense, this is a little bit weakening because if we want this ability to be able to take any data structure and convert it to an oblivious counterpart and do it maybe more efficiently than log n. So this is sort of the line of work that I took in, which was sort of, can we circumvent the lower bound, right? We know that oblivious RAMs can't go beyond log n overhead, but are there ways to circumvent the lower bound in certain ways? So I'll tell you several things that I tried, and I'll tell you what happens. So one first way that you can think about circumventing the lower bound is the fact that an oblivious RAM stores data with only one trusted server, right? When I gave you that picture, there's just one server. But a standard thing we do in crypto is suppose, let's say, we distribute the trust amongst multiple servers. Maybe there's 10 servers, the adversary can compromise at most 1 or 2, and the other 9 we know are safe. But we don't know which ones are trusted or not. So let's try this. Let's suppose we have something called a multi-server ORAM. I'm going to outsource my storage to, let's say, 4 servers. One of them is adversarial. I don't know which one is, right? If you know which one is, you can clearly ignore it and just use the rest. So we don't know which one it is, but we know there's a most one. So what happens is in this model, anytime you interact with the adversarial server, the adversary sees everything, right? So whenever you do this, it sees everything in the storage here as well as sort of whatever you interact with. But anytime you interact with any of the other servers, the adversary has no knowledge, right? So as an algorithmic, like if you're building an algorithm or you're building an oblivious RAM, this makes it a lot easier, right? In the sense that you have 3 servers that you could interact with for privacy in terms of free of privacy, while one of them is compromised. So you could think there would be hope here, right? The answer is no. So what we quickly proved actually is that in the CellPro model, multi-server ORAMs require logarithmic overhead. And in fact, it's really bad in the sense that you would think, okay, maybe it's true for 2 servers, 3 servers. In fact, it's true even if there are polynomially many servers and only one of the servers are corrupt. So let me explain what this exactly means in that let's think about the 2 trivial constructions you could consider for a multi-server ORAM. There's one approach which is simply pick one of the servers at random and hope the adversary is that's not the one that's corrupted by the adversary, right? And then use like your plain text array search. This will give you a constant overhead, but you only get obliviousness with probability 1 over the number of servers, right? So if you have polynomial number of servers, this is not enough for cryptography typically. This is too weak of an oblivious notion. Then there's another approach, which is simply ignore every other server, pick one at random, and do an oblivious RAM with it, right? This gives you logarithmic overhead, you get the obliviousness you want, but I'm not using the power of the multiple servers. I'm literally doing a single server. So going back to our lower bound, what we actually prove is there's nothing in between. Somehow, these 2 constructions are the best you could achieve, and in a sense, nothing else can happen in between, unless you have an exponential number of servers. I don't know how, that's not realistic really, right? Okay, so that didn't work. So that was my first attempt. It didn't work, so let's try something else. Another reasonable approach, or maybe before I go, any questions on this? Yep. No, log n total. But like, if you think about it, it's better to have it with 1 server because that actually makes it more efficient than having it. Go ahead. Good. Let me think. The idea essentially is that the trick essentially is in these lower bounds, you need a very, like specifically for this one, you can show that there's from the single server lower bound, the adversary needed a piece of information. It turns out that the piece of information you only need it with probability 1 over poly n. You can show that you can morph whatever the adversary needs to mount the best attack towards an ORAM. It still works even when you only have a very partial amount. So think of like something like a PCP, for example. You need to check certain properties of it, and you can check a very small fraction. And that's still sufficient to mount an attack with very high probability, essentially. With attacks better than this probability, because I can't do better than this, obviously. But yeah, we can talk more later. I can tell you more about the details if you're interested later. Any more questions? All right, so that didn't work. So let me try a different approach, right? So one thing is that when you note about the oblivious RAM definition, it inherently protects against all different sequences of operations. Maybe that's the problem, right? You have, if I have 100 operations that differ in 100 locations, I need to be able to make sure they're both indistinguishable from each other. So we can do maybe sort of a differential privacy style approach, right? Protect only operational sequences that are similar. Maybe you have 100 operations, but they only differ in one location. Okay, this could be interesting, right? Because maybe that's how the real world works. We know most of the time that, I access the same things over and over again, and there's only a few things that are very sensitive that you want to hide from, right? So let me formalize this. So let's consider a differentially private. We'll call this a differentially private RAM. So what happens in an oblivious RAM is that let's say you had one sequence. The second sequence that you want to hide from can differ in every location, right? So here's 5 and 5 different operations. We could instead consider a differentially private RAM where only one operation is different here. Right? 4 of them are the same and 1 of them is different. Okay, so how do we define this? I'm going to use I don't know. The definition here is not that, it's a little complicated if you've never seen it before, but in terms of essentially you're going to use this thing called epsilon delta differential privacy and use this formula. And the reason we use this formula, if anyone wants to figure out why, is that it allows composition. Right now, these definitions only consider sequences of operations that differ at most one operation, but really you want this to extend to like k operations, and sort of by making sure you satisfy this specific formula, you can make sure, for example, if they differ at k locations, you multiply the parameters by k, which is not the best composition theorem, by the way. You should use better ones in the future, but it sort of allows you to get some reasoning about operational sequences that differ as wide as you go. So in other words, what you want is, if operations are very similar, you want to hide them. The further away they get, the less privacy properties you want. Right? So this is much weaker than an oblivious RAM. Okay, so this seems hopeful, right? I spent, before we're hiding 5 sequence, 5 or 10s or hundreds of operations, and they all have to be different. That seems hard. Hiding one operation, it should be easy. I spent 6 months trying to do the upper bound, and it turns out there's a lower bound. So for some reason, even when you try to go to something so weak, something so obviously much weaker that you should be able to do something, you still can't. So what we ended up proving was that, in fact, when your epsilon is constant, so you typically want epsilon to be constant and delta to be much smaller, but even when epsilon is constant and delta is less than some constant, it turns out differentially private RAMs still require logarithmic overhead. Okay, now you may ask, what if you have multiple servers? Yeah, okay, it doesn't work. You can do the same thing again, where essentially, even in the multi-server setting, the same results sort of hold. Okay, so this was a very surprising result for me because I spent 6 months trying to do it. Like, I literally thought the upper bound should be within hand, and it took us a long time and we couldn't do it. So, all right, what else? You could try other ways to do this. So, for example, one interesting way to circumvent the lower bound would be that reads and writes don't occur at the same frequency, usually, in most systems, right? You do more reads than writes. So it's okay, maybe reads require sort of maybe writes would require logarithmic time, but reads might require sublogarithmic time. That might be okay, right? So this would be one way to get around this, and no. Oblivious RAMs are really painful. No in the sense that you really suffer. If you make one of the reads or writes sublogarithmic, you make the other, I wrote super logarithmic, but it becomes exponentially larger. The trade-off here is not great. This doesn't somehow work either. These oblivious RAMs are really painful. They started, they're in a sense, all of these approaches have been trying to reduce something, right? The previous approach was trying to reduce privacy. Here I was trying to get a trade-off. And somehow oblivious RAMs, they just are not allowing me to do anything. Okay, so let me try a different approach, which is more on the lines of encrypted search. So far, what we've been trying to do is sort of lower the privacy, right? Or maybe have a trade-off between read and writes. But everything else, multi-server differentially privacy, was all about taking an oblivious RAM, making it weaker, and trying to see if I can get a sublogarithmic construction. Let me try a different approach, which is more of an algorithmic approach. Take a construction that's efficient but insecure, and try to upgrade its privacy, right? Maybe the reason is because an oblivious RAM is such a high notion of security, I'm just not going far enough down. So let me go from something I know has sublogarithmic constructions, try to work my way up, right? And this is how I got into encrypted search. So this notion of encrypted search is very related to an oblivious RAM, but let me explain to you what it works. It's very similar in the sense that rather than it being arrays, it's more about indices or key value stores. But okay, let me give you the motivation of what encrypted search is. Encrypted search is the idea that you want to sort of outsource a corpus of documents to a third-party server, but allow search. So what that really means is essentially creating an index, a search index, over the documents locally, and then encrypting it and sending it to the server in such a way that the server can't learn what the index is or what kind of operations you're reading and writing from the index. It's very similar, actually. When you look at it like this, it's actually very similar to an oblivious RAM, even though the works are somewhat different in the literature. Okay, so let me get into the definition. It turns out that for encrypted search, people care much more about efficiency than privacy. So they don't have such a strong notion of privacy here. In particular, they define encrypted search where they're allowing this thing called leakage. So, okay, it's going to be a little weird, but let me get to it. You can define some leakage function L that takes as input any sequences of operations. And essentially, what encrypted search inquires is that for any sequences of operations such that their leakages are the same, so L0, L01 equals L02, in this case, you want the adversary's view to be the same. So another way to view encrypted search essentially is taking the operational sequences and partitioning them into many spaces. And within each of these partitions, you want obliviousness. Okay? So obviously, how you define the leakage function and how you partition the space will determine how weak or strong of... Yes, go ahead.
By leakage, you mean the amount of information?
Exactly. So essentially, that's this. So essentially, how to formalize this essentially is something like, yeah. So exactly what you're trying to say is, yeah, what is so learned by the adversary. So L will be an upper bound on what the adversary sees, and if any two sequences give the adversary the same output or the same leakage, they should be indistinguishable from each other. That make sense? Okay, so let's compare it with the previous notion. It turns out for an oblivious RAM, you can also define it via leakage functions, where the leakage essentially is the length of the operational sequence, right? What an oblivious RAM says, it says any sequences of the same length should be indistinguishable from one another. So you can define the leakage to simply be the length of the operational sequence. In practice for encrypted search, it's not this. It's far more complicated, has many, many things, and it's usually non-trivial and much, much larger than O, because you really want to partition the space to get much less than logarithmic overhead. All right, side note, someone might ask is, how about differential privacy? You can't define differential privacy using leakage, right? Because what is differential privacy? Differential privacy is giving you like a spectrum. Everything all the points that are close by have some privacy notions. Whereas leakage is partitioning and asking for perfect privacy within each partition. So this is good for us in the sense that we know differentially private RAMs cannot have logarithmic overhead. And the fact that leakage can't do this, maybe this is the reason why we can get the sub-logarithmic overhead, essentially. Maybe it's okay to, instead of having this sort of spectrum of privacy across many nearby things, if we just partition, we might be able to get something. That make sense? All right, so let me give you, sadly, I would say sometimes, one of the state-of-the-art encrypted search schemes, which is called this hash encrypted compiler. So let's try to figure out, if I wanted to do something to allow you to do searches over these indices, what is one trivial way to do this? Well, you take a private key and you hash the keys. So you have a deterministic hash for each of the keys. And you do a randomized encryption for the values. All right, I said I'm starting from something very insecure. This is very insecure, right? But it works. It's at least this adversary can't see what the encrypted index looks like. So just to make sure it works, if you wanted to read cat, what would you do? You upload a hash of cat. And you download this, and you can get the encryption and decrypt, right? And if you wanted to write, well, I just send a hash of cat as well as the encryption of 1. The adversary finds the thing and updates the encryption, right? I'm not telling you this is private. I'm just saying this is one way to do this, where you get something. And you get constant overhead. So I promise you, I'm starting from something very inefficient, from something very efficient and insecure and trying to upgrade, right? All right, so let's try to upgrade this, but to upgrade it, we need to figure out what it leaks. So what is the leakage of the hash and encrypt compiler? Well, you can quickly see that for every single read and write operation, you're leaking a hash of whatever you're reading, right? And the adversary doesn't know it's a cat or a dog, but it can group them together or color them. Oh, I'm not sure if the coloring you can see, but sort of, you can see that the cats are colored one thing and the dogs are colored another thing, right? Formally, how this is usually defined is via a matrix. So you have a matrix where, each of the operations are put in the rows and columns, and you have a 1 if and only if sort of they're the same. You're querying for the same key. So all the cats have the same 1s, all the dogs don't, and so forth. So dog will, cat will, but dog cat won't. Okay, all right. So this is probably not very secure. I don't know. So let's look at our goal. We've been trying to lower privacy. Let's try to take an inefficient but efficient but insecure construction, which this looks like, and try to upgrade its privacy, right? So what could we do? Right. So let's try to remove some of the query equality leakage, right? We essentially know when two queries have the same key or not. Let's try to remove a little bit of it, just a little bit. All right. So the first step we try to do is, what is the smallest amount of leakage we could remove to make the problem somewhat interesting? This is what we came up with. Maybe you guys can come up with something else, but essentially what we want to do is this thing called decoupled query equality leakage, where we decouple the read and write operations. So now, even if it's a read or write, let's say there's a read of cat and a write of cat, they're for the same key. So one of the most minimal things we could do is remove that coupling. So instead of having the reads and writes be the same color, let's hope we could do something else where we color cats, writing of cats to be different than reading of cats. Right? Now, I'm not telling you why this is private. Again, this doesn't seem to be private, but it's a reasonable thing to study, right? Because taking something that we know can be done in constant time and just trying something a little bit harder, a little bit more private. So we do this for cat. Similarly, dog will also be recolored. But critically, I'm going to make, because I'm trying to make this as easy as possible for me, the two dogs for read are still the same. So the adversary can still see that. In other words, what I've just done is taken the reads and writes and split them off. You get the key equality within all reads, you get the key equality within all writes, but I don't want it between read and writes. Again, I don't know why this is private or why this is useful, but it's interesting to study. Okay, so we should be able to do something, right? No. Again, somehow, as soon as you do that, you can prove a lower bound, that you're back into logarithmic overhead. Which, again, very much surprised us because of, I don't know, what did we do here? We didn't even do anything, right? Like, so maybe there's a reason why all the encrypted search schemes are stuck there. There's a good reason for it, actually, right, in a sense. If you try to do literally, I can't think of anything weaker than this. It's not even a meaningful privacy notion, and you're stuck, right? Okay. Yeah, so that's sort of where we are today. So I promised to give you the limitations of all of these techniques, and that's where we're stuck today in the sense that an oblivious RAM is this very, I don't know. There's many words I would like to call it and insult it, but it's this very annoying thing that somehow we know how to do it in logarithmic overhead with very strong privacy. Yet trying to get anything weaker than it seems almost like a useless task at this point. So, but doesn't mean we should stop. I'll give you some open problems at the end. But what I'm going to do now is go and give you some proof techniques about how we proved all of these things. Go ahead.
I guess you can't. Be slowed down to hold.
Yeah, I mean, given everything I said, probably yes.
Yeah, okay.
I mean, I don't even know, like this is so weak that adding differential privacy on this thing, let's say you could do it, it's not meaningful,
Yeah, okay.
right? Like this is already too bad, right? Yeah, not even interesting if possible, right? Like, I think the outcome from this is essentially, it's not that we were coming from the wrong side. Coming from either side, you really get stuck in that sort of where the state of the art is they're there for a reason in a sense, the constructions. And sort of all of these limitations are telling us why we're there, essentially. Okay, so I think Max asked as well. Now it might be interesting for you guys to understand where the hardness comes from, right? Sort of giving you a taste of the techniques. So I'm going to go through one at a very high level, with not too much detail, but I'm sort of hopefully try to give you guys the ideas of where sort of these privacy notions come in and why it makes it so hard to construct algorithms, essentially. Okay, so let's go through this. In particular, there are like two or three main techniques to prove lower bounds. The one I'm going to go through is actually the oldest. It's from 1989 by Friedman and Sachs, called the chronogram technique. And in particular, what we're actually doing is taking data structure lower bounds from non-cryptographic settings and sort of somehow bringing them into cryptography. So what you do in standard data structures is leverage the hardness of the problem, right? You're going to use the properties of the problem to make these to prove that the data structure has to have high overhead. Instead, in our works, because if I'm doing an oblivious RAM, what are you going to do? The problem's easy, right? Instead, what we're doing is leveraging instead the properties of privacy to make these more challenging. So in a sense, the techniques are the same, but how you use the techniques end up being quite different. All right. So the chronogram in cryptography has been used, I think, 4 times. I think all by me so far, but I'm going to talk about the easiest one at this point. But okay, I'll mention that in cryptography it's used in these 4 papers. In outside of cryptography, it's used in many, many places. Like it's used for many, many data structures. So it's not like it's a technique. Sort of the adaptations are a lot of our work, but the original technique is from Friedman and Sachs in the 1989. There've been a lot of imaginative ways to use it so far. Okay, so if I'm going to prove a lower bound, what's the first step? Come up with a hard distribution, right? I need to pick a hard distribution and show that under this hard distribution, that's randomized, the data structure must have logarithmic overhead, or I'm going to break some properties that the data structure is supposed to maintain. So for us, the lower bound is really simple, actually. I'm going to write random blocks to the end entries in order, and I'm going to read one of the random ones I just wrote. That's it. In particular, remember it's a differentially private RAM, so I can only allow sequences that differ in one location. Critically, all the hard distributions differ in exactly the final read. Okay? So in fact, this satisfies this, and in fact, all I'm going to do is make sure all of these have to be somewhat similar. Okay, so let's now partition the write. So I'm going to sort of organize the hard distribution in a way that makes it easy for me to intuit and reason about. And in particular, what we're going to do is we're going to break it down into these epochs. So the epochs have different sizes, and they start off largest from my right, from your right, and they decay exponentially towards the left. So this is the largest with r to the k writes, and the last epoch has only one write. Right? So I wanted, just for simplicity, just remember that the epochs are numbered in decreasing order, just to make the r to the k be the number of writes. So the largest epoch is the highest number 1 appearing at the very beginning of the operation, and the epoch with the lowest number 0, with the smallest size, is appearing at the end. Okay, so how does the lower bound for differentially private RAMs go? So we're in the cell probe model, so the server has a bunch of cells. What the adversary is going to do is simply number them. And I'm going to number them in the following way. So during the operational sequence, every time you overwrite a cell, I am going to number it. I'm going to change this number to the epoch that you had, that was the operation, the epoch containing the operation that last overwrote the cell. So what I've done essentially is saying, okay, the top left one means that an operation in the 5th epoch was the last one to overwrite the contents of this cell. And because the adversary is sitting there forever, it can actually do this, right? It can number every single memory cell like this. Okay, so, well, why is this interesting? This allows us to sort of categorize where information is stored, which is how we're going to prove our lower bound. In particular, for example, let's just say I'm going to fix an epoch, in epoch 5. And what I want to do is figure out where the information, during epoch 5, I did r to the 5 writes of random blocks, right? I want to figure out where is this information stored? Where could it possibly be stored, right? If the data structure is too efficient, it can't be writing everywhere. So therefore, the information about epoch 5 must be very localized into a small number of places. So let's figure out where it can be stored. Well, obviously that, if you overwrote a cell during epoch 5, you probably wrote some information about epoch 5. So therefore, everything that's written about epoch, every cell that was last overwritten in epoch 5 could contain information about epoch 5. Same thing is true for all the information of all the epochs that occur after epoch 5, right? Because if I read something from epoch 5 and I write it into another cell in epoch 4, it could have information about epoch 5. It's not the most efficient way to use your stuff because you also have information about epoch 4, but it's possible, right? So these are two different places. So epoch 5, all the operations that occur after epoch 5. Remember, the epochs are indexed in reverse order, right? So the 0, 1, 2, 3, 4 occur after epoch 5. And the last place the information could be stored is in the client memory, right? I could just always store it there and stuff. And in fact, this is it, right? This is everywhere because I'm assuming that the blocks are generated at random during query time, right? So there's no correlation between them. So there's no way for writes that happened in the past to write about things that occurred that I just generated during epoch 5. So there's 5 places, and now we can simply analyze how big these are, right? In particular, let's look at these two, right? I had arranged these epochs in this weird exponentially decaying way, right? So I'll tell you why now. Let's think about why. In particular, these are decaying, but let's say we have epoch 5. Let's look at all the epochs that happen afterwards, right? Because they're exponentially decaying, they're much smaller. The number of operations that occur after epoch 5 is, a factor of r smaller than epoch 5. And in particular, we're supposing that the data structure is very efficient, right, for our lower bound. So therefore, it can't read to or write to too many cells during the updates. So therefore, if you play with, so it contains at most r I minus 1 updates. In particular, if you play with the parameters a little bit and you make r depend on the update time, and you assume the update time is sublogarithmic, you can quickly show, in fact, that you don't have enough time, you can't touch enough memory cells to encode more than half the information you generate during epoch 5. So epoch 5, you generated a bunch of random bits that you wrote into the array. You can quickly show that even like, it's obviously not going to happen, but this is the worst case, that if the data structure just focused on epoch 5 and use all of its future times just to focus on epoch 5, it can store at most half the information from epoch 5. So there's half of it still missing. And in fact, okay, so then the next part is client memory, right? Or first of all, maybe I should, does this make sense to everyone? Essentially, there's not many updates, right? The updates, there's 1 over r fraction less updates.
Oh, you mean everything that came after?
Everything that came after epoch 5, yes.
But
Yeah.
if you include epoch 5, of course, everything's...
Exactly, yes. Essentially, all I'm trying to say is that this can't contain too much about epoch 5. This usually doesn't, it's just small, right? Client memory is usually a key. Like you can store 128 bits, 256 bits, whatever. It's much smaller, therefore we can simply ignore it. Okay, so there's 3 places that can store location. 2 of them don't contain much, therefore one has to contain everything else if you're correct, right? So it must be that the cells last overridden in epoch 5 encode at least the remaining half of the information, and usually much more probably, right? Okay, so what does this mean? Well, let's try to use correctness first. Let's say I picked the x, the index x to read, to be a uniformly at random from one of the r to the I writes in epoch I. And I want to be correct, obviously. I want a correct data structure. Well, what does that mean? Well, it literally means that with probability half, I'm going to most likely get some information that you haven't encoded anywhere else. So therefore, you must probe at least one cell, last overridden in epoch 5, with probability greater than a half, right? And I haven't used privacy. It's purely correctness so far, right? I haven't done anything about privacy. So here's the secret sauce, essentially, the secret ingredient. Let me consider, let's say there's k epochs. Let me consider k experiments, right? I have done this experiment, and I looked at each of these individually, right? What do I know? For any of these little things on the side, I know that if I had chosen that index just for correctness, I have to probe a cell that was last overwritten in epoch 1 with probability half. Same thing for 2, same thing for k, right? Well, you can quickly show that this is true. This must be true for all epochs simultaneously, regardless of the query. And in particular, the idea is simply, let's suppose you don't query a cell from a specific epoch. With high probability, I can tell you you didn't query from something from there, right? Just from correctness. If I know you're correct, right, which I'm assuming you are, then you couldn't have queried from it. You couldn't be correct and query from this epoch at a time, right? But if you don't query from it, and you're like correct, then I know you just didn't query. In other words, you end up breaking differential privacy. So in particular, let's look at it carefully. Let's suppose you never query a cell last overridden in epoch 10. Then the adversary can quickly determine that most likely you did not read a cell overridden in epoch 10 as long as your data structure was correct. Does that make sense? And in particular, it turns out that, maybe going back to Max's question, this is a very small amount of, like it's really small, right? Like even if you hid a large portion of this thing, it turns out you can still do something where the adversary can sufficiently guess this, essentially. So it turns out, yeah, so this is actually all you need for this specific lower bound for differentially private RAMs. And in many cases, what ends up happening is you sort of, if you weaken the adversary in terms of what it sees, either you have to prove more sophisticated adversarial algorithms that work with the privacy notion. And actually, in some results now, there's like these things called snapshot oblivious arrays or snapshot oblivious RAMs where the adversary is weaker as well in the sense that it doesn't see the entire sequence of content. Like it's not sitting there forever. It only sees portions of the operational sequence as they're executed. You can even sort of prove things where the adversary doesn't have the numbering on the server side even. Let's suppose you only had a small set of numberings. It still works even. All right. Any questions? Very good. So the way we chose is that these are exponentially decaying. So the number of epochs is logarithmic. The number of epochs is logarithmic, and you have to read one cell from each epoch. Sorry, I guess I missed that, but that's exactly where the bound is. You have to read from one of each of these guys. And all of these, so one thing I wanted to mention also is they're all disjoint. They partition, right? If I prove that you're reading a cell last overridden 5, there's no interference with ones that are last overwritten in 4, right? So if I prove that you need to read one of each of these things with a different number, that's enough for you to prove the lower bound, essentially, of logarithmic. Make sense? Sorry, I missed that. I guess I should put that in. Okay, so since this is the theory department, I'm assuming you guys might think about, you guys might want to prove your own amazing lower bounds about why ORAMs are really, really annoying to deal with, right? One thing you could do is go through our techniques and do this, but it turns out we actually created a framework for you to make this a little easier rather than you having to understand all the details. So in a work at, I guess, Eurocrypt this year, my co-author, who's appeared very often in these pictures, Pino and I, actually proved that you can actually do this while only thinking about 2 very specific properties about the privacy and data structure problem you're considering. So we actually show that a framework where you can get logarithmic lower bounds in the Selpro model when your problem and privacy satisfy 2 things. They have to satisfy these things, obviously, otherwise there's nothing you can do. But sort of the first is that the queries have to be sufficiently complex to enable retrieving information. So arrays allow you to retrieve information. If you had a data structure problem where I said return random bits, you can't prove a lower bound, obviously, right? You need to have the queries need to be somewhat sufficiently complex to have some information being written and then read. And the second thing essentially is we sort of generalize all these privacy notions and show that we can define these things through something called an event transfer probability, where what we show is that if an adversary observes events for one set of sequences of operations, it better do it with some probability for another sequence of operations. In a sense, this is exactly what we're talking about for all these privacy notions, right? We're saying, obliviousness means they have every pair of operations to hide. Differential privacy says if they differ at one location, all of these things. So sort of these sort of quantify exactly the basic necessities needed for our lower bound. And of course, I'm saying in the sense that if you can't satisfy one of these things, then you probably can't use this, because if you have no privacy, you shouldn't be using our techniques. And if you have a data structure that doesn't need to do anything, well, you could probably trivially satisfy them. So I'm not going to go into too much detail, but sort of I'll give you the steps if you wanted to prove your own lower bound. So for the first thing, this large information retrieval, it's very similar to what I had shown before about finding a hard sequence of updates, right? In particular, what you have to do in step 1 is you literally pick a random update sequence, U1, U2 to UN. But this has to satisfy specific properties. In particular, for any consecutive set of updates, you have to be able to show, so let's say UA to UA plus L, so this is an L bit L updates. You have to show there's a corresponding query set whose size is order L, whose answers have high entropy with respect to the updates. So let's make this clear. For an oblivious RAM, this is obvious, right? In the sequence I showed you guys earlier, I literally wrote a random entry to block 1, to block 2, all the way to block n. So for any consecutive sequence of subset of updates, the corresponding query set is just to read the L overwritten blocks, right? And clearly, whatever random things I wrote there are what are going to be read, so they have high entropy. But now you can use your imagination for many other problems as well to apply this, essentially. And you can get more and more complicated things. In fact, you can show these kind of things also hold for, let's say, I think we showed for set membership, union find, predecessor successor, so a bunch of algorithms, data structures that are studied in algorithms can be shown to satisfy these things. And sort of this is the formal notion of what we say essentially is that, what I really want is that the answers, given the updates, given all the updates except for the ones that you're considering, should have high entropy. All right, does that make sense? It's very high level, but I promise you it's not hard to satisfy once you think about it. So the second one, essentially what we say is that for any update sequence U and a query Q, so a read query Q, it better be that if you have an event E that's observable by an adversary, there should be some probability it transfers to a different read query Q prime. But lucky for all of you guys, we have a bunch of generic lemmas. So if you wanted to consider obliviousness, differential privacy, multi-server, encrypted search, forget, you can just use our other lemmas. But maybe this could be interesting in the sense that if you want to consider new privacy notions, it's sufficient to simply show that this very, very simple definition is satisfied for your privacy notion. So sort of, these are the only 2 things you need, and we show that it's enough to get logarithmic lower bounds. All right. right, so, okay. I have questions, but I have time. So I want to give you some open problems because I've only talked about lower bounds, right? Like, it sort of feels like I'm waving a white flag saying, let's give up. Let's just stop working on constructions and make our whole life about lower bounds. But I would actually like to say that there's actually hope to still circumvent the lower bound. In some of these cases, I can provably show that we can't even prove lower bounds. So therefore, there's hope. So let's look about it. There's two ways I can think about for oblivious RAM and encrypted search. One is this idea of read-only versus read-write. So I think this was a question you asked earlier, which was, does the ORAM allow writes? And the answer is yes. But you could consider a read-only ORAM, right? You have the data structure to be fixed. I construct it, I leave it there, now you only read. So this is easier. Okay, one thing I also want to point out is, if you think about all our lower bounds, they do a bunch of writes. So for example, the chronogram I showed you, it does n writes followed by one read, right? So it's somehow critical that we do a bunch of writes for all the lower bounds. And in fact, I can tell you that every lower bound I know of must do essentially omega n writes to be able to prove a log n lower bound. So even if you try to prove these things, like the lower bounds don't go through. And in fact, there's a reason they don't go through. There's great work by Weiss and Wicks in 2018 at TCC. They showed that suppose you proved a read-only oblivious RAM lower bound, logarithmic. In fact, not even logarithmic. Let's say you prove something super constant. Then you would be able to rule out the existence of small sorting circuits or very efficient locally decodable codes. So this is not a reason why we couldn't prove read-only oblivious RAM lower bounds. But if you do, write it as sorting circuit lower bounds or locally decodable code lower bounds. No one cares about read-only lower bounds. But sort of this is a barrier, right? In terms of, in TCS, the community, we're stuck at these lower bounds. We don't know how to prove superlinear sorting circuits lower bounds. We don't know how to prove locally decodable code lower bounds very well. So in a sense that it would be very surprising that proving a read-only oblivious RAM lower bound allows you to break these barriers. So in a sense, this is sort of hardness of read-only oblivious RAM lower bound. So the open problem I would give, first of all, is that, is it possible to design read-only oblivious RAMs with sub-logarithmic overhead? We can't prove lower bounds, so there's hope for upper bounds. I don't know how to do it. It's a very good question. It could be very useful in practice. But I actually want to give you an even more stronger open problem. Let's suppose instead, like I told you, all the ORAM lower bounds or these lower bounds require you doing a linear number of write operations, right? So there's nothing ruling out the fact that you could design an oblivious RAM that has sub-logarithmic overhead for a small number of writes. Let's say square root n or even log n. So maybe you have a budget. I allow you to write log n or square root n up in writes. Afterwards, maybe I don't give you privacy. Maybe I don't let you do any more writes. But is it possible to sort of develop sub-logarithmic overhead ORAMs in these models? Make sense? Any? So there is hope. There is hope, and I will not be proving lower bounds about this anytime soon. So therefore, we should try to prove upper bounds. The second one, which I think is very interesting, is we assume sort of the original reason why I gave you ORAM was because of this composition, right? In a sense, you can take any data structure, blindly apply an ORAM, and get logarithmic overhead. But you can ask yourself, is that the best way to do it? Right? Maybe sometimes the data structure is complicated, but in a privacy-preserving way. So therefore, you can combine it and get the ORAM maybe for free, right? So maybe the idea is sort of amortizing the cost of privacy across many queries when you have more complicated functionalities. So, here's a problem I would like to give. So I told you there's an ORAM composition theorem. And here are two open problems, of which I actually don't know how to solve either of them, which is very surprising to me. Can you find any natural data structure that has overhead T without cryptography and design an oblivious variant that beats ORAM composition? Right? Or vice versa, pick any other natural data structure problem that's not a stack, queue, array, or something very simple where we know these bounds, something more complicated than that, and prove that ORAM composition is optimal for that data structure problem. To my knowledge, I don't know of any of these. The only ones we know type bounds for this are essentially arrays, stacks, queues, deques, which are not very interesting. They're not really amortizing the privacy across multiple queries. They're just really one memory access. All right, so I'll give you a specific problem that I've thought about. Okay, anyways, before I do that, here are some bounds that we know for other data structures. So there's like oblivious, stacks, deques, queues, search. oblivious new neighbor search. Actually, I didn't add this, but Eurocrypt this year we showed this for also problems like set membership, predecessor successor, as well as union find. But in those problems, we only proved a logarithmic lower bound. And all of these have like near constant overhead in plain text land. So they're not exactly what we're looking for. And for new neighbor search, it's not logarithmic overhead. In fact, the best algorithms we have are n to the epsilon. So think of like square root n. Even without cryptography, the best bounds that we know of are order square root n, and we only prove a log squared n lower bound. But that means in plain text land, apparently new neighbor search, the best lower bounds are just log n. So this was an improvement over that. Now, I want to give you a specific problem I thought about for a long time that I think is interesting. And it's this partial sum data structure. So what is it? It's very simple. You still have an array of length n. The writes are the same. You just overwrite the ith entry with x. But the reads are a little bit more complicated. Essentially, the reads, what they do essentially is, if you want to read for some index I from 1 to n, you return the partial sum of all the entries from 0 to I. Okay? And it's well known, since for like a decade. Oh, am I out of time? Okay. Anyways, yeah, this is the open problem. If I'm out of time, we can. But anyways, this data structure has logarithmic overhead in cryptography, and the question is, what's the right overhead in oblivious for oblivious partial sums? Is it log squared? Can you get something better than that? It's not known. And this is an open question that I think is very interesting. I think that's it, yeah.